Good afternoon, everyone. So we are here for the PhD defense of Chloe Gutteridge on magnetism and settings of stars in front of a jury composed by the following members. So on my right, we have Connie Ernst from the University of Leuven, and he is one of the two referees. The second referee is Thorsten Bohn from Iraq. On my left, Victoria Vicky Antocci from Denmark's Technische University, and then Pascal Petit from Iraq, and then the two co-supervisors of this PhD thesis, so Claude Catalai and Coralie Meyer. Chloe, you have about 45-50 minutes to present your work, and then we'll have questions for about an hour, and then we will deliberate, and I will ask everybody to leave the room, and then we will come back for the final defense.
So I'd just like to first start by thanking the jury for not only reviewing my manuscript, but also attending all in person, which is honestly above and beyond what I was expecting. And today I'm going to be presenting my last 3 years of work on magnetism in pulsating stars. So to start with an introduction into the topic, hot stars drive galactic evolution. They're a major influence on the interstellar medium, both during their lifetimes with their stellar winds and their disks and their large radiation outflows, but also in their supernova deaths. These supernova deaths will then trigger further star formation, pushing forward new generations of stars with higher massivity. These hot stars sit in the top corner of the HR diagram, being both the hottest and the most luminous, and exhibit strong variability. Those mass outflows I talked about, and radiative instabilities causing X-ray shocks, rotation due to various features on the surface or in the circumstellar environment, binarity. Approximately 90% of these stars do come in binary with binary companions. And then finally, and most importantly for me, pulsations. Because when I said they sit in the corner of the HR diagram, they don't necessarily sit there stationary. In fact, their color does change with time, which is in turn the temperature changing, and to an extent the magnitudes too. The magnitudes being what we tend to detect. So these stars primarily oscillate in 4 key regions. The first being the sets up here, the slightly cooler SUVs below, then down to the cooler delta Scutis, and then finally to gamma. Beta sets and SPBs are similar in that they both are excited by ion opacity, but the restoring force is different. So in beta Ceph stars, this is pressure, but in SUV stars, this is gravity. These cause different frequency ranges. So beta Cephs have many more cycles per day, whilst SPBs only have a couple to less than 1 cycle per day. In the slightly cooler range, you have the delta Scutis and the gamma Dors, which are often considered analogous because they both share a similar excitation mechanism, although gamma Dors do have an additional component of collective blocking. But they have, in delta Scutis, the same pressure restoring force as beta Cephs, and in gamma Dors, the same gravity restoring force as in SPBs. In delta Scutis, this causes a slightly higher typical frequency than you would have for beta Cephs. Whilst in gamma Dors, it's approximately the same as what we find in an SPB. These oscillations are dependent on the stellar structure and the properties of the star, with different modes probing different regions of the star. So the gravity modes probing down to the core, whilst the pressure modes look at the radiative envelopes. Oscillations do not necessarily occur alone. There are many examples of hybrids, which are very powerful for what we're about to go on to talk about astral technology, because we're able to probe both of these regions, the radiative envelope and the collective core. So astroseismology is taking these oscillations that we observe and working backwards to reconstruct a stellar model which could cause the pulsations that we see. These can give us precise determinations of mass and radius and age, which are very key for any study that we're doing. But then it's also the only way we can directly measure internal structure, internal rotation profiles, core overshoot, and the minimum internal magnetic field strength we can expect to be in the core. So when performing this, there's a very useful set of tools in photometric surveys. Several of these have existed over the years, starting with MOST, and Coro, Kepler, Bright, and now thèse, which is what we use currently. So, as well as stars, OB and A stars being oscillators, they're also approximately 10% of them magnetic. We found this out through several large surveys of these stars, MINDS, Dynamics, and BOF. These fields are predominantly strongly dipolar, approximately 3 kilogals as the median field strength, and they lie oblique to the rotation axis. They're stable over long time scales of basically as long as we've been able to observe them, which is 70 years approximately. And this leads us to believe, based on Occam's razor, that these are fossil fields. So dating from the epoch of star formation, these fields became frozen into the stellar structure from the cloud the star formed from. We expect dynamo fields in the convective cores as well. And these fields have been shown in models to be amplified by the surface magnetic field. And regardless of if these fields are at the surface or inside the star, we know that they modify the stellar structure and the evolution of the star. In the inside, this is affecting chemical mixing and the rotation profile due to the angular momentum transport. But then also at the surface, they drive features like solar winds, which also feeds this angular momentum transport. So there's multiple ways we can detect a magnetic field in a star. The first being the indirect diagnostics. So these stars are often chemically peculiar, so showing too strong helium lines or too weak helium lines than standard. There's also the 52 angstrom depression, which is due to metal lines, which are brought to the surface by magnetic fields. And then there's rotational modulation. Rotational modulation due to these chemical spots on the surface, often near the magnetic pole. As these magnetic fields often oblique to the rotation axis, it rotates in and out of view, creating a nice curve showing that we can expect there to be a magnetic field. These magnetic fields, however, can only be properly detected by spectropolarimetry. Once we have field measurements from spectropolarimetry, but they can go one step further and we can map these surface magnetic fields through Zeeman Doppler imaging. The Zeeman splitting gives the magnetic field strength, the Doppler effect gives the velocity and therefore the position on the stellar surface. And from that we can reconstruct what the magnetic field on the surface of the star should look like. Now we're doing this all with the end goal of performing magnetoastroseismology. So this is performing astroseismology with the additional constraint of having magnetic fields. We know that magnetic fields have effects on the pulsations, so they decrease stochastic excitation in the core, stabilizing low order P modes, suppressing high order G modes. So the selection of the modes depends on the magnetic field inside the star. We know that they modify the pulsation cavity itself, which changes what modes we can expect to see at the surface, and it modifies the period spacing of these pulsations quite significantly. So What we can do is by taking into account these magnetic fields, which modes are present, which modes we would expect to be present if there wasn't a magnetic field. We can start providing constraints on the mixing we can expect in the interior, the rotation profile, and the interior magnetic field strengths. This has previously been done for red giant stars, but this is a very new method of study for OBA stars. So to date, it's been performed on 3 different stars. The first being Beta Ceph, which is the prototypical Beta Ceph star. However, the results from this I will discount just on the incorrect rotation period being used. At the time, the correct rotation period wasn't known until a couple of years later. V2052 was the second star. Now, this was mainly standard astroseismology being used, but using that, they found inhibition of mixing inside, which was consistent with the critical field strength, which was in itself consistent with the surface magnetic field extrapolated into the interior of the star. The final one being HD 43317, which was studied 2 times, this latter of which resulting in a measurement of the near core magnetic field strength for the very first time in a B star, which was 5 times 10 to the 5 Gauss. So we now know why we'd want to do this. So to be able to perform magnetoastroseismology, the first step is having stars that we know are magnetic and we know are pulsating. So I ran 3 different observation campaigns. The first looking at TESS, Beta Ceph, and SPB pulsators. So we classified so the Mobster collaboration classified these as northern Southern hemisphere OB stars that showed G or P or both pulsations in their TESS light curve, along with rotational modulation signals indicating magnetic fields present. And this resulted in 38 stars being selected. The second one was literature known magnetic stars. So this was again came from the Mobster collaboration, and they took OB and A stars with magnetic field detection in the literature, went and looked at their TESS light curves to identify G and or P mode pulsations. They selected only those visible with CFHT, and this so that we could characterize the magnetic fields of these stars. And this resulted in 36 being selected. And then the final sample was Plato hot pulsators. So in December next year, we expect the launch of the Plato space mission, for which they're accepting complementary science missions. So to prepare for this launch, I searched in the Plato LOTS 2 field for OB and A stars that had G and P pulsations and rotational modulation in its light curve, to then perform magnetic detections on them and propose it for the Plato space mission in the future. This resulted in 47 stars being selected. So to take you through an example of how the data is processed, we take a star from the sample. So in this case, it's a sample 1 star, so identified by the Mobster collaboration. This star was observed in TESS sectors 14, 40, 41, and 54. And it shows we have the G mode pulsations here. We have the P mode pulsations up here, which are much lower amplitude. And then we have rotational modulation signal up this side. The rotational modulation frequencies suggest that there's 2 possible rotation periods, frequencies of 0.09 and 0.18 cycles per day. But we can tell from the splitting of one of the G modes that we can expect it to be 0.09 cycles per day from the separations in the splitting. So once we have chosen a star, we then have to choose the correct instrument to observe it with. The first option is Neonava, which is in Pictomidi. it's a 2-meter class telescope with a resolution as standard of 50,000, but with the super resolution algorithm, it could be increased to 65,000, and it covers the full optical range. The second option is Espedon's at CFHT in Hawaii. This is a larger telescope at 3.6 meters, has a resolution as standard of 68,000, and also covers the full optical range. Then the final option is Harpspoll, which is down in the southern hemisphere in Chile. It's also on a 3.6 meter telescope and has a high resolution of 110,000, but comes at the cost of having a smaller spectral range. So once we choose an instrument to propose it to and they grant us the time, we then obtain the data and we have to reduce it into something we can detect magnetic fields in. So from the telescopes, from the reduction team there, we get 3 spectra. One which shows circular polarized light, which is the Stokes V. One is a null diagnostic, which is the N. And then one is unpolarized light, which is the I. If we can see a significant signal in the Stokes V without any signal in the Stokes N, and this lines up with the Stokes I, we know that there's a magnetic field. Now, doing this for individual lines requires an incredibly high signal-to-noise ratio in the spectra. And this is where a tool called least squares deconvolution comes in, which essentially creates an average of the individual lines that are hand selected to not be blended, not be affected by other more sensitive things. And once these lines are selected, they are averaged into a much higher signal-to-noise diagnostic, which is what we do here. So applying this to the star I showed the test frequency spectrum of, we observed the star with Espedon's and reduced it using the LSD methodology I just went through. And this gave us a nice clear Stokes V signal, no clear signal in the null, and it lines up with the Stokes I profile. And this then results in a magnetic field measurement of 335 Gauss. And this was the first magnetic detection in this star. What's also interesting in this profile is we see a little bump at the bottom of the I profile, the unpolarized light. Now this is common in both magnetic and pulsating stars. So if there is a transiting feature, such as a spot, we expect to see a decrease in light where that spot is, causing the little bump. In the case of pulsating stars, they can create a very similar effect by the Doppler shifts. So if a star is moving in a certain direction, slightly more this way, slightly more this way, and not so much in the middle, you can create a little bump. Which one it is, we don't currently know because we only have one observation. So further observations will be taken for this star to determine the field geometry, first of all, because we only have a single magnetic detection, but then also to determine the line profile variability origin. Is this pulsations? Is this spots? So looking at my full sample one, we observed 22 stars. I redid the test frequency spectrums for each of these stars with the sectors that had been taken since the first classification was made. And this resulted in 10 SPBs, 10 SPB beta hybrids, and 1 SPB delta Scuti potential hybrid, and 1 star that was reclassified to only have rotational modulation in those that were observed. We had magnetic detections in 6 of these stars, 1 of the SPBs, 4 SPB beta Ceph hybrids, and 1 suspected SPB delta Scuti hybrid. This gives us about a 27% detection rate, which is well below the 70% we'd expect from previous work using rotational modulation as a pre-selection tool. However, what needs to be considered is that we may have a lower detection rate in SUVs, but the detection rate in SUV beta-Ceph hybrids is much higher. And this could potentially suggest that the likelihood of an SUV beta-Ceph star, hybrid star, being magnetic is higher, and potentially the probability of an SPB being magnetic without being a hybrid is lower. However, we are working off of very small numbers here of stars. Now we go on to sample 2, which is stars that we knew were magnetic already, and we took multiple observations to try and characterize their magnetic fields. In this sample, we observed 8 stars with neonava. These were 5 SPBs, 2 SPB beta-Ceph hybrids, and 1 suspected gamma dor. This resulted in magnetic detections in 5 stars, which were 4 SPBs and 1 suspected gamma dor. So these SPB beta-Ceph hybrids this time don't seem to have any magnetic detections, which maybe disproves the previous hypothesis in sample 1. And we have non-detections, which would not be expected in the 2 SPB beta-Ceph hybrids and the 1 SPB. Now, these stars were known to be magnetic, so it's quite concerning that we didn't get magnetic measurements when we know that the thresholds we were observing at should have been capable of detecting these magnetic fields. Since the neonaval instrument was installed at TPL, there have been concerns raised about the quality of the data released. In sample 1, if I quickly go back, all but this final star here was observed with neonaval. Then we have the non-detections here, which may suggest that instead of there being some link between the types of stars and the magnetic detections we can expect, instead it may just be the data from neonaval is not good enough quality to give us the magnetic detections. So for these first 2 samples, I consider these stars that have non-detections as not being magnetic, but rather not being magnetic enough to be detectable with the instrument we read. So sample 3, which are my Plato-Hopf pulsators, we observed 24 of these stars with Harp's Pole down in Chile. This was 6 beta-Ceph stars, 4 SPBs, 8 delta Scutis, and 6 suspected gamma dors. We had magnetic detections in 5 of these stars, which were 3 beta-Cephs, 1 SPB, and 1 suspected gamma dor. We curiously had non-detections in all of our delta Scutis. Now, going through these by hand, a number of these were binaries, so it's likely that the signal in the test spectrum from the transit of the binary was mistaken for rotational modulation. We expected a lower detection rate with Harp's Pole, so we can't use this to compare detection rates against the previous 2 samples, because Harp's Pole has lower efficiency than the other instruments. And also, during the observations, the Plato field was at a high air mass, and there's only a certain degree to which we can compensate without going over the limit of how long you can take observing a single star. So now to look at these results in the context of all known magnetic classical pulsators, that being beta-Cephs, SPBs, delta Scutis, and gamma dors. Those that I've put in bold are the ones that I have detected myself for the first time. This shows that there's very few stars that have been detected to have both magnetic fields and beta-Ceph pulsations. It's just these 2. Now, there could be multiple causes to this. The first being that O stars are not very common, so the likelihood of them having both of these characteristics at the same time is then even smaller. There's also O stars have relatively few spectral lines in the optical range, so we're less capable of being able to detect magnetic fields in these stars. To be able to determine whether O stars are just less likely to have magnetic fields and pulsations simultaneously, we'll need future generations of instruments that are capable of going down to lower magnitudes or capable of going into the UV. But all of these stars appear to be located in the standard instability strip. That's not including magnetism, which can cause changes in the position of the instability strip. Moving on to the beta-Ceph SPB hybrids, they are many. They're definitely overrepresented. And this could potentially suggest that the SPB pulsation strip is being extended up into the beta-Ceph range, causing these hybrids to exist. As we do know, magnetism should affect the position of the pulsation instability strip because it modifies the pulsation cavity. If we go into the SPBs now, there's still a large number of SPBs without P modes. So just because this instability strip is being extended upwards, it doesn't mean the entire instability strip is being shifted. We are still seeing SPBs down to cool temperatures. Then onto delta Scooties. I won't go into depth here because I only looked at one delta Scooty, and that was a hybrid with an SPB. We know from previous work that delta Scooties were found to be pulsating at hotter temperatures than we'd normally expect if they had a magnetic field. So it shouldn't be surprising that we found an SPB delta Scooty hybrid, because we know that many magnetic delta Scooties are B stars. However, we can't confirm currently if it is an SPB delta Scooty hybrid because we only have a single observation of it, and we need to confirm it's not a binary system. There's no evidence in the photometry that it's binary, and there's no current evidence with our single spectrum for multiple lines indicating multiple stars. But we potentially have a single line binary, and we need to be able to have multiple observations to disentangle that. Then we have our two potentially magnetic gamma doors. Now, again, I'd like to say the same disclaimer here of we don't know if they are definitely gamma doors, because they could be binary systems like the SPB delta Scooty hybrid, with one star being magnetic and one star being a gamma door. Previous examples of this have been found. But with that disclaimer out of the way, if we consider the hypotheses that these are single stars, we have a rotational modulation signal, we have G modes, we have a temperature that is hotter than we would expect for the gamma door stars, but too cold to be an SPB. So we should expect that these are gamma doors being moved to hotter temperatures due to the magnetism that they host. In both of these stars' cases, they have over 1 kilogauss fields. They are very, very strong, and were previously found to be magnetic in both cases in the literature, and classified as APB-T stars. So now that we have a selection of magnetic pulsating stars, we now need to understand their magnetic fields and characterize them and map them. So to do that, what we would like to do is Zeeman Doppler imaging, which I briefly mentioned at the start. For Zeeman Doppler imaging, there's multiple different codes that we can use. There's standard ZDI with no abnormal behavior of the star, for which a common code used is ZDI pi. But then there's other codes available. For example, if the star is rapidly rotating and becomes late, there's a code by Kang et al. And if the magnetic field is decaying, for the cooler stars with dynamo fields, there's the time-dependent fields code by Finocity and Doherty. But all of these previous ZDI codes assume two assumptions to be valid. The first is that surface brightness is constant with time, which is not true for pulsating stars. And secondly, rotation contributes, only rotation contributes to the surface velocity. We also know that not to be true in pulsating stars. So in pulsating stars, if they are slowly enough rotating that they're not oblate, which would need the oblate code to deal with that, we know that the surface brightness variations are negligible when measured, when their effect is measured in the surface integrated line profile. However, we also know that the surface velocity varies non-negligibly, and this will cause variations in line profile, such as these, to be incorrectly attributed to permanent features in the surface brightness, when in reality these are velocity features from the pulsations. We know that the models only converge in the first place if the amplitude is low. If the amplitude of the pulsation is high enough, the code just doesn't converge on the solution at all. If it does converge, the solution is incorrect, and it's an effect of the degeneracy between velocity and spot variations. So what we need is to map the velocity of the surface of the star to be able to understand how pulsation is contributing to the shape of the line profile. To do this, we have a line model, which is a Gaussian local line, which is weighted by the local brightness, which is the brightness map you saw on the previous slide. This local line will be Doppler shifted by a local velocity, which is contributed to by both the pulsation and the rotation. This is then weighted by the projected area of the surface element of the model and summed over the visible surface, and then divided by the sum of the projected surface area weights. So in this, we need to fit the brightness map, we need to fit the line widths, and then we need to fit this new velocity map. So to consider the velocity coming only from pulsation, we have several individual parts we need to fit. The first is the overall velocity, which is then split between the radial and the tangential components. And then this is given a phase for each individual mode. So per mode, we have to fit 3 different parameters. Mode identification is then done separately, well, is done previously with another tool such as Soutenance in the current version of the code. This gives us a velocity map. This is only showing pulsation here, which modifies the line profile. But it also modifies the Stokes V profiles that we can expect, because Stokes V is dependent on Stokes I. So making magnetic measurements without taking into account how pulsation is affecting that is inherently incorrect. Any residual line profile variations after pulsation has been taken into account are assumed to be from permanent features such as spots, because we have to remember these 2 things can exist simultaneously, and especially in the case of magnetic stars, which are often chemically peculiar. So to test our code, we first start with a simulated beast of Ceph star with a uniform surface brightness and a dipolar magnetic field. We give it a completely blank surface brightness map. We compare to ZDI pi, which does not take into account pulsations, and the code does not converge. When run with our code pins, pulsation-informed magnetic mapping of stars, only very small noise-like features appear in the map, which are not high enough amplitude to cause any issues with the magnetic field modeling, which I show here. So We run ZDI now, assuming that it had produced the infinite surface brightness to be able to compare if the magnetic field is alone a good enough representation. And we see in the radial field, they all look approximately the same. But when you go to the azimuthal and the meridional components, we start to see quite a strong deviation from ZDI pi, which shows that our code is absolutely necessary. We can't just assume a uniform surface brightness to avoid the problems with the code converging. We run this test a second time, but this time we give the surface brightness spot. ZDI pi once again does not converge, but PIMS recreates the spot, but with a slight blurring around the edge. The blurring decreases with the more observations you give, especially in the phase where that spot is visible, because it's able to reconstruct the very crisp edge I gave it in the input brightness map. We once again run ZDI pi, assuming that it had correctly reconstructed that spot. And we find once again that the radial field is largely consistent with one another, but the azimuthal field and the meridional field are incorrectly reproduced by ZDI pi. So the PIMS code is absolutely necessary for mapping the magnetic fields of pulsating stars. There is an error here of just short of 70 Gauss between the input and what is reconstructed for the dipolar component of the field, while for PIMS this goes down to 11. This gives us much more accurate magnetic field maps, which will be needed for magnetoseismology in the future. So to consider the observation requirements, we have tested this for an SNR down to 250, and it's still able to reproduce the magnetic field accurately. So the SNR is much more likely to be a requirement for getting a magnetic detection than it is for being able to do to be able to run the PIMS code and get an accurate result. Because 250 is roughly for a strong side of normal magnetic B star that's polar, has a low V sin I, which is scales the exposure time by a factor of itself squared. The rotation phase must be covered, but the pulsation phase is more flexible. This is because we're not measuring the pulsation parameters. We're not finding what L and M are in this code. So we don't need to see the full phase. We just need to see enough that the code is able to hook on to the right point of the phase. Rotation phase, however, must be covered as in every ZDI code, as if you don't see all sides of the star, you can't expect to be able to map all sides of the star. If we consider the rotation pulsation period ratio, so each line here is one complete cycle. If you observe a star like a SPB, which often has its rotation period be very similar to the pulsation periods, if there's not enough differentiation, what you can find is you're observing at the same point. For each rotation phase you're observing the same point of the pulsation phase. This makes it incredibly hard for the code to determine what's coming from pulsations and what's coming from permanent features. So in these cases, what we need to do is increase the baseline of observations to be able to get this differentiation. We know that low amplitude modes can be ignored. If a mode's amplitude is low enough that it's not significantly affecting the line profile, then it's not significantly affecting the line profile. You don't need to consider pulsations when mapping the magnetic field. We also know generally that more data is needed for the more complex mode geometry to be able to correctly hook onto the correct phase. And also more data is needed for more modes, as it's more likely to get confused between two similar. So to try and quantify this required number of observations, I ran 2 tests. One is on a beta Ceph star, based off of the beta Ceph star V2052 off, using the known pulsation frequencies and mode identification. And I then gave the code an SPB star, which I gave a rotation frequency incredibly close to the pulsation frequency. In both of these cases, I give a rotation frequency of 1.1 cycles per day and spots on the magnetic poles, as is common in these magnetic stars. So for the beta Ceph, what we get is largely the same as standard ZDI. Because we're not doing mode identification, we don't actually need as much data. However, with the SPB star, we require many more observations. So that's 109 if we only look at one rotation phase, because we need that many observations to be able to disentangle what's permanent features and what's the pulsations. And even at 109, it still doesn't quite correctly reconstruct the brightness map. If we're to then split it over 6 months, this halves it, but we're still incredibly close in the frequencies. And if we were to randomly spread it over 6 months, that goes up to 68, which is considerably higher than standard ZDI. And unfortunately, this is the most likely scenario in what time we are granted by the time allocation committees. But these only work as guidance. The number of observations will be different for each star. So now if we go to applying this to a real star, we carry on using V2052 off, but the real star, the real data this time, rather than simulations. V2052 off is an oblique star, has an oblique field that is off-centered and dipolar, and it has helium spots near the magnetic poles, which makes it a good candidate for testing multiple different aspects of common magnetic beta Ceph stars. It has 3 known pulsation modes, including the radial mode, and 44 Narval observations, which was the predecessor to neo-Narval, that cover the rotation and pulsation phases very nicely. This was the subject of previous astroseismic study as well, so being able to get a good magnetic field map means that we can start getting even more precise astroseismic measurements than were obtained before. So to start, I took a look at the test frequency spectrum, which I pre-whitened, to reveal different frequencies and see if there was any that had been missed, because the mode identification was done back in 2012 before TESS had launched. And we see F1, F2, and F3 as standard, along with the rotation frequency and its harmonics. But we also see this mysterious F4, which hadn't previously been identified. However, because it hasn't previously been identified and we don't have any more spectroscopy or spectrocalorimetry, we can't perform mode identification on it. So I will prefix this by saying any results here is subject to the fact that we haven't considered one of the pulsation modes that are present. So first we'll take a look at the brightness map for all lines used in the LSD spectrum. What we see is a dark spot, which we would expect near the pole of the magnetic field, but it's looped round to the other side. This is due to ZDI being not a perfect modeling method. You can have multiple models that reconstruct to the same test statistic of accuracy. So there is an imprecision here in the brightness map that needs to be considered. Our further observations would be able to better disentangle and result in hopefully removing this ring feature. So when we look at the magnetic field, we constructed this for 3 different sets of LSD data. The first including all the lines, the second only including the helium lines, and the first discounting all of the helium, last discounting all of the helium lines. And this creates quite different models. So between all lines and the no helium lines, the main difference is the beta value, how oblique the magnetic field pole is from the rotation axis. However, in helium lines, this starts to cause the pole to actually be much more diffused. So how do we choose which of these models is the best? What we do is we look at the chi-squared statistic iterating over inclination. This created, for all lines, the black circle set of data. For the helium lines, the blue crosses, and the orange triangle for no helium. We then look at the error bars with delta chi-squared and 3 sigma line. And what we have come to the conclusion of is we prefer the all black helium model. Now, this is due to the minima being, first of all, much more neat. This is very, very spaced out due to multiple minima all stacking together in the all lines section. But also because what we have in the helium lines is a breaking of an LSD assumption. If we include helium, we are including the helium spot, which first of all is damaging the brightness map, but also it's a chemical spot, which means that not all lines are being formed in the same conditions, which is a very key assumption of LSD. By removing the helium lines, we're not completely removing this effect. However, the effects on other lines is secondary to the helium, which is coming from a different altitude within the stellar atmosphere. So to conclude, I have performed ZDI over magnetic pulsators for the first time by developing the pulsation-informed magnetic mapping of stars code pins. There's future development of this code also planned, which will include mode identification built in, so we're able to consider the magnetic field selection at the same time as doing mode identification. We will also consider breaking the current rule, which is the pulsation axis must be the same as the rotation axis. This is because we know in stars such as rho P stars this is not the case, but currently we did that to avoid having quite so many parameters we're having to fit simultaneously. I then took this PIMS code and applied it to V2052 off, the first data for it to be applied to, and created to date the most accurate magnetic field map for this star. We're also looking at going further than just one star in the future, obviously, because we have observations that I have taken characterizing these magnetic fields, which hopefully we can use to map the magnetic fields using PIMS. And there's also archival data, like we use for V2052 off, which in some cases sufficiently cover the pulsation and the rotation phases to do PIMS magnetic field mapping. And one of these cases is Z2CAS, which I am currently applying it to. I also have characterized magnetic OB and A pulsators. So I discovered 10 new magnetic OB pulsators, potentially discovering pulsations in 2 already known to be magnetic stars. So these could potentially be the first magnetic gamma dwarfs, but once again, we need to make sure that these are not binaries first. I have found that there's a high number of hybrids among the magnetic detections, with the potential of discovery for the first time of an SPB delta Scuti hybrid. Once again, we need to confirm this is not a binary system, but it wouldn't be unexpected to find a magnetic SPB a delta Scuti hybrid, as we know the delta Scutis are being pushed up towards the SPB instability strip due to the magnetic fields. This would be the first observational evidence in B stars of the instability strips being pushed hotter, so SPBs being pushed up into beta sets. So on to what we can expect now in the future. There's lots of opportunity for observations of these stars in the future, to be able to perform magnetoastroseismic study on large ranges of these stars. So the first being the Plato space mission, which I'd already started preparing for, which launches in December 2026. This will have a better cadence and a better baseline of observations than TESS, making our results much more precise and allowing us to go up into even higher frequencies. But also the magnitudes that Plato works at are very useful for spectropolarimetry, because we can usually go down to about a magnitude of 10, but I prefer those to brighter due to having higher signal to noise for shorter exposure time. And we do with fast cameras, and potentially with a saturation extraction code, where we'll be able to go up to a magnitude of 3 or 4. I've also begun preparing for the northern field. So after 2 years pointing at the southern field, they will take the option to turn Plato around to point to a northern field. If that's the case, I already have targets in the northern field that would be able to be proposed for a complementary science mission. The next is the Amakiki Community Survey. So this is a co-mount of espadons, which I already use with FIUM, which is a spectropolarimeter in the IR, using a optical device called Wenea-Cal. Within this community survey is work package 5, which focuses on stellar magnetism and evolution. And I am already contributing targets to such a survey. We already have a list prepared. And this will allow us to characterize magnetic fields of more stars and also obtain detections of more stars. Then going on to further into the future, we have the Viper spectropolarimeter, which is something being suggested for the VLT at ESO. So this would be down in the southern hemisphere, where we have relatively few instruments, but would cover a spectral range from the IR into the optical, and at a similar resolution to what Paris-PSL does currently. So similar resolution, much higher spectral range. This will be able to increase the number of O-star magnetic detections by going for stars that are dimmer, being able to get a higher SNR in stars that we can currently observe, meaning we can get down to a lower field threshold. And it would also be capable of detecting magnetism in the LMC and SMC. So we'll start to be able to look at how metallicity affects these pulsating magnetic stars. And then finally, there's the option of UV spectropolarimetry. So there's several missions already planned, Pollux, Polestar, and HWO. So these will be able to give us spectropolarimetry values from the UV section of the spectrum, which is where most of the lines for our OMB stars are, which with more lines, we're able to get a better SNR and obtain better magnetic detections. We'll also be able to look at other features, such as the UV resonance lines that are coming from these stellar winds. So we'll be able to study both the environment around the star as well as its magnetic field. With all of this, both coming from my thesis and future instrumentation in the future, we'll be able to perform future magnetoastroseismic studies, look at individual stellar properties for individual stars, with measurements of their internal magnetic field strength, information of inhibition of core overshoot in more than just one star, and the enforcement of rigid rotation and other features. Because I've identified many hybrids, we have many very good candidates for doing this, as we'll be able to probe down to the core as well as the radiative nebula. And we can now perform magnetoastroseismology at a better precision, thanks to the PIMS code giving us a very detailed identification of the magnetic field at the surface of the star. We also enable, once we have multiple of these, to move on to doing population studies. So we can look at the observational positions of the instability strips already, which means we can see how the magnetic field is modifying the selection of pulsation modes. But then we can start looking at how internal properties are being changed with temperature and mass and rotation rate and all of these things that we're measuring with magnetoastroseismology. And finally, we'll be able to obtain what typical values for an internal magnetic field strength is, which is currently unknown for our stellar evolution models. So we'll be able to obtain much more precise stellar evolution models and understand the evolution of these stars. I'd like to thank you all for listening.
So now it's time for questions. So I could really start with the library. So first of all, like commentary, that's the question.
Interesting work, which really has a lot of effort put into it, and so also a lot of potential. So then we dive straight into your analysis here. You have shown an immense amount of observations that you have included in your thesis. So as you said in your talk, this requires applications, convincing time allocation committees, doing the observations, doing the analysis, and then you can start interpreting. So it wasn't clear to me from your manuscript, did you do all this for everything you showed?
So excluding the very first observation proposal, I was PI for every single one I've included in my manuscript. So the first two samples were selected by the Monster collaboration, but I redid the frequency analysis for all of the stars I've included because these were done in the early days of TESS back in 2020 predominantly. So there's many more sectors that have now been taken, and I'm able to get better values by redoing reduction. So I did all of that, and then I reduced all of the spectra to using LSD.
So one thing, one advice that's impressive, and I sort of, it doesn't jump out of your manuscript. So can you please revise that and make it very clear, and even better so, include one or write one big publication with all these observational facts. That's one thing that I have nitty-gritty details on your first chapter. I don't have time to go over them, even though I've just started, but I will hand over and then I hope you can take them into account. But there's one thing I would like to discuss with you. You have much more courage than I have, in the sense that you search for magnetic signatures at the surfaces of stars, which is a hard problem, as we have heard. I'm an astroseismologist, and as you rightly indicate in your first chapter, observational signatures in both rotation and magnetism sit in the pulsations of stars, right? Could you say, how can you recognize, as a seismologist, that a star has a particular internal rotation? How do you do that?
So what we tend to do is we look at the splitting. Okay. So just around this one mark here, this is a G mode. There's one that's been missed because I limited the number of frequencies to 50, so it picked the 50 most significant. But these are all split by roughly 0.9 cycles per day, which is largely what the interior rotation rate should be. What needs to be also considered is magnetic splitting also exists. So I can't say yet that that's what the interior rotation is, because I need to take into account that magnetic.
Yes, and so I think it's correct to say that in all of what you did in your thesis, well, not in all of, no, let me retract. There is a difference between having a magnetic field aligned with the rotation axis and inclined. And the one test star that you took is a beta-Sep that I know very well. And it has an inclined geometry.
Mhm.
Right? Now, what would an inclined geometry potentially offer aside from rotational splitting? Do you know that?
If I remember correctly, it changes the amplitudes of the splitting
Yes,
components.
it changes amplitudes, but
So-
there's something else. What you have here is literally like this, putting my hand.
Yeah.
Why? Why are there 5 peaks
Oh, because
Yeah.
of the geometry.
of the
Of the
which geometry?
The right. The geometry of the pulsation mode
Yes, but
carrying
it's
from L.
yes, coming from L because of rotational splitting.
Yes.
What does an inclined magnetic field potentially
It
offer
gives
you?
a additional.
Yes, exactly. So how many peaks can you have in principle? Sorry, I didn't hear
That's
that.
what you're asking.
So in
Sorry.
principle, rotational splitting of a quadrupole mode gives you 5 peaks, right?
Yes.
2 plus 1. Let's
Okay.
imagine we add an inclined magnetic field.
Mhm.
Can you get something else in that case? Then 12 plus 1 peaks?
So I haven't done this yet.
No, I know.
So,
She
but
may
my
be under confidence.
understanding was it would change the separation of the
It can
peaks,
change
but
the
it wouldn't
separation.
change the number.
Yes, it can.
Okay,
Okay.
okay, thank you.
And so that's actually what we seismologists hunt for, in addition to you. So I think that's valuable information for your thesis, and it's one of these things that I will hand over. Okay, moving on. I'm going to have to be selective because of time reasons. Let's see. Yes. One case that you also discussed is HD 43317. No need to go somewhere. I'd like you to be a bit more precise in your text because you're listing this as a star with a confirmed magnetic field, right? And that you take from the literature, so it's not your work. I very strongly prefer you to say that this magnetic field is not directly detected, it's inferred from mode suppression.
Okay.
Right? And so the authors did that from a particular mode identification.
Mhm.
And I can tell you that I'm responsible for that mode identification. And I don't trust my own. So please be aware that if the mode would be incorrectly identified, then this inference is wrong. And I think
And
this
there's
is
been work to show that
this-
there's very many ways you can incorrectly identify modes.
Yes, you understand, you and I are on the same line.
Yeah, yeah.
Okay, so that's just a caveat. For all your stars, actually, this would be of importance. Then I move on. Let's see. Yes, something I like very much in your work, because it confirms what we also find in a completely different way, is that there is actually not a clear distinction between all these instabilities.
Yes.
And actually, you may want to look at a paper led by Dan Hay. We actually find that the whole main sequence is one big instability with densities that are very different. And something is making us, realize that instability computations are incomplete. That's also what you find. In your case, you assign it to magnetism. There may be other things like binarity.
And I think it was a paper you were involved with
Yes.
the Gaia mission that
Yes,
shows that
exactly.
none of these pulsators Gaia is identifying a full length wave.
Yes,
expected.
exactly. So this is something I think you find in your way in a very different way. Please make it clearer in your manuscript that this is actually very nice complementary information, because I know that theoreticians get upset when you touch their instability strip, but they have to learn to live with reality. And I think your thesis is an important point. Yes. Moving on. There's so much that I can. Yes. Could you go to your solution slide for V2052 of UP? where you discuss these helium lines and the fact that, yeah, the solution with or without helium lines is perhaps different.
Would you like
The
all
table
of
with
them
the final,
or-
no, the table. I think you showed it, yes, this one, okay. Here's a comment that you might not like, but I'm asking it anyway. You, in all your solutions, and I'm not even talking about the 3 different ones, if I look at that angle beta and its error, then given it's an inclined field, I take note of the fact that 55 degrees is an inclination, is an angle of complete cancellation. Right, so you have geometry and each of these, you're assuming a dipole field, right? And if your beta is 55 plus or minus something, then your signal is really in a degenerate state. I don't know if you realize that.
I didn't at first, but what I will say was with both of these two, I really do not trust the beta angles or the inclination angles, because we're seeing that the ring spot appearing.
Yeah.
We really can't trust, because what's underneath is not very good. When it comes to here, so the errors are purely based off of iterating over inclination.
Yeah.
So we haven't varied so much the beta keeping the same inclination.
Yeah. So
the error bars on that could be better.
Okay. So let's say I am not yet convinced. How could you convince me with the data that you have and the tools that you have that I don't need to worry?
So what I'm going to say is do worry, honestly. We've been joking that this isn't so much the best model, but rather the least worst model. We don't have enough data to deal with the fact that the spot is looping around on itself. We don't have the mode identification for one of these modes. There's potential error in these modes. There's lots of the LSD assumptions broken in those two. If we use that one, we're still having a secondary effect. We don't expect that to be major, but we haven't tested it. There's lots and lots of places error can come into this. So my honest answer is it's not amazing, but what it is the best we can currently do with the current data we have.
Okay, let me add something in addition, because this is a beta set, so it's model data, but still in recent findings of our pulsation theories, we have found that actually if as of 20% critical rotation, the oblateness is also a key point.
Yes.
And I think that's not in your PIMS model right now.
It's not in my PIMS model right now. That's partly why we selected the star. It has a rotation period of just short of 4 days. It's nicely below that 20%, so we're not having to deal with oblateness.
And so how difficult would it be to include that?
So
is that a few weeks work? Is that a few months or a few years?
If I was just to include an oblate geometry in this code, a month maybe. That it's not a large job to do. However, the oblateness then affects the pulsation modes.
Yes.
Yes. So
I know.
Yeah. Then you need 3D modeling, and we've come over there doing his work to be able to build a background for this code to be able to build off of that. We're far away from being able to deal with oblate stars.
Yes, I agree with you on that one. I just wanted to check if you realize that, and obviously you do. I guess can I have one more thing? Yes. Yeah, this is on page 65, a quote. You don't have to look at that. You're right that as the pulsation axis is forced to be parallel to the rotation axis, this causes deviations in the line profile based on inclination, right? That's what you write at some point. And so my question then is, isn't this a reason to let go, that these axes are usually aligned?
Yeah, so I think in the bit you're reading, I talk about, or maybe a bit earlier in that section, I talk about that this F4 mode could actually, there's a mode,
Yes,
if I was to use a lower
yes,
signal to noise threshold, it's roughly equal sides.
Yeah.
I think the F1 frequency, which could imply that there's
Yes.
rotational splitting happening here,
Yeah.
which would, if it's the radial mode, mean that it, like, so either we misclassified that this is the radial mode, or the pulsation axis isn't aligned with the rotation axis.
Yes.
I found that in this star.
Yes.
I think you found in Beaton and Seth that
Yes.
there's a potential that's happening there too.
And now we have a third star that is not yet in the literature. Well, it is half, but it's normal that you didn't spot it.
Yeah.
It's again a beta set, and we are very, very sure it's not aligned.
And do you know
That's
if it's
3
like,
out of 3.
yeah.
It's still small number statistics, but maybe there's a trend here.
Yeah.
Right? So that's something you should.
I'm not sure if I'm allowed to ask you questions, but do you know if it's magnetic? Because
It's
could
not
we be-
magnetic at the surface, but I don't care about that.
Yeah.
It's magnetic in the interior.
I was just
Because
wondering
we
if there's
see
a connection with the
we
Moraine.
see 9 peaks in a quadrangle, and you
Okay.
cannot get that from the
Yeah.
lid.
Yeah.
Whether theoreticians like it or not.
Mhm.
So anyway, that's just a nice remark for you maybe to take on board if you publish this one point. And then I think I have yeah, maybe a last short question if I may.
Yes.
So you have done procedures, huh? You start from magnetic stars, you hunt for pulsations. You start from pulsating stars, you hunt for magnets. And then you did Plato, which is future. It's not so easy. That's what the conclusion of your thesis is also, despite tremendous observational efforts, right? How can we make this more efficient? What's the very best way, according to you, with your expertise, to do next to make it more efficient to do magnetoastrophysics?
This is currently in place, but missions like thèse are absolutely brilliant because it's a full sky survey pretty much. There's small areas that haven't been covered yet, but that means we now have down to, I think, something like 22 magnitudes, and like observations of each star, which is well beyond what we can do with spectropolarimetry. So one of the things is getting more spectropolarimeters, getting down to lower magnitudes, so we're able to see more stars. We have a couple of IR ones now, but we don't have any UV currently. We have those the missions are currently planned. So getting those instruments up so we can go to different wavelengths, which are more appropriate for the stars we're looking at. Being able to go down to lower magnitudes, having more options because the competition for the suite that we currently have is incredibly high.
Okay, thanks. That's it from us. Thank you.
Thank you.
Thank you. And Thorsten.
Okay. Well, Chloe, let's say some general words before we go to the details. I enjoyed a nice and clear presentation. Especially, I like the introduction and I like also the observation part. I must say I'm very happy since the manuscript was a little bit written in a hurry, and I will come to that later. But I was very positively surprised or encouraged by this presentation. I like it. So okay, I think your subject is very interesting, and it should be developed further. So it's just a starting point, and you have a lot of very interesting stuff to do. You built a tremendous database. You did a lot of work, and I think you should be less humble. You should just push a bit more what you did. You did so much, and you don't see it in the manuscript. I mean, you did the observations, you did the application for telescope operation, for telescope observation time. You did data reduction. We will come to that back a little bit later. You did so much work, and you are too modest, humble to show it. So you should more clearly exhibit what you did, this huge amount of work. So concerning the manuscript, I think I don't want to go too much into details. I gave you a list of lots of remarks. They are missing many things like headers and captions, which are not as they should be, error bars, window functions, and so on. I don't want to enter that. It's not really interesting, but it would be largely enhanced your manuscript if you could add that. Okay, it's not a substantial criticism. It's just a question of presentation.
Yeah.
Okay, so. There's one point where I'm extremely interested in your vision. I discussed it also with your PhD supervisors before. Independently of the fact that I think it's a very interesting approach to take into account the stellar pulsations on the surface in order to model in a better way the magnetic maps. And this is really interesting to be done, that you did that, and that you continue to improve this PIMS, and that's very nice. I still wonder about I mean, this is a result as it's on itself. So you always cite the word of magnetoasteroid seismology, and you make a kind of implicit link between the stellar surface magnetic field and what's happening inside the star. Two things. I mean, there's one person who's called Matisse Stefan, who wrote in 2021 in his paper that there's no link basically between surface magnetic fields and what's happening inside, from a magnetic point of view. On the other side, there's also a paper by Lee et al. For the year in Nature, where they discovered by indirect analysis of the pulsation modes inside the star, they conclude on a strong magnetic field of 1300 kilogauss inside the star. And when they checked the surface magnetic field on that star, there was nothing. So they didn't see any kind of, they couldn't detect it. Okay? So my question is, and I think I know some part of the answer, but my question is, do you think even if there's a possibility of linking these surface fields by some way to the internal fields, or which kind of steps would be required, if ever?
So the first thing I think I should clarify is we would expect to find stars with an internal magnetic field that don't have a surface magnetic field. We believe these fields are coming from different origins, so there's no reason why you should have the surface magnetic field in all stars, and the internal magnetic field in some, not having an internal magnetic field in some stars. So in that case, we're saying it's not coming from its formation conditions. We're saying the dynamo field that's happening in the center, we should have those conditions in all of the cores. We should have a magnetic field there. So that's the first thing I feel like I need to clarify. There's different works, some saying that we shouldn't see an effect of the surface magnetic field on the internal field, some saying we should see that the surface field is amplifying the internal field. So really we need to model different situations. We need to take observations, model what we should expect from different situations and see what matches up there. I try to be careful not to pick a side in this argument, because I don't do the modelling of the internals. I don't know fully, I don't comprehend fully exactly what goes into each of these different versions as models. What I can say is, just on observations, that we know from astroseismology that we can expect to have internal fields. We know from spectropolarimetry that we have surface fields. So it's very important to explore the combination of the two. Can we expect the propagation inside? Can we expect the propagation inside to actually be destroyed by the motions inside the star? Is rigid rotation allowing for that propagation to happen without it being destroyed, etc.?
Okay. I think this deserves a very long discussion.
Yes.
We don't have the time here, but it's an interesting point to be considered. And we should probably just think that if we have a perfect knowledge of the surface field, that we can infer some strong constraints on the internal field. I mean, this link is not so easily done. As I understood, one of your major ingredients of your PIMS model are, of course, the characteristics of the pulsation modes. And I understood that you use FAMIAS. I know this tool.
So I
Was all Miss Piquet used it, yes, right? That used that data, fine, fair enough. I think, having used myself, FAMIAS, it's not so easy to apply it on each kind of star. So probably it's really interesting what you suggested, that you want to model it directly in your PIMS. But then of course you need tremendously high quality signal to noise data, because otherwise you will have so many parameters to be fitted that you might not converge. I presume. What do you think about that?
So I have thought about this. First of all, yes, PIMS alone has a huge number of parameters as is, so trying to include further ones is going to be a challenge. What I've considered is supplementing with further data. So yes, I'm providing it with spectropolarimetry, but I'll also provide it with spectroscopy just to look at the pulsation modes and phase that with the spectropolarimetry for the magnetic field. I'll also consider photometry of, well, we can expect frequencies here, so you need to be searching in this sort of for the frequencies assigned with pulsations, because we know from photometry it's there. So it will take a lot more data to be able to fit all of these things simultaneously. The more that we try to fit, the more risk of degeneracies there are. But there's ways to provide more data without it having to be spectropolarimetry, which is hard enough to get hold of as is.
It will be a challenge. In your chapter 4, when you apply for the first time PIMS to real data, I personally have the feeling that it's quite difficult to conclude on the major improvement of.
So the results I got were very much consistent with the work that Coralie had gotten back in 2012, using a dipolar model that was off-centered. My field strengths, if I consider the dipolar component alone, which is what I use for comparison, are very, very much consistent with what Coralie got.
That wasn't my question. Sorry.
What we do have is the meridional and azimuthal components, which weren't obtained before, and we do have multipolar components.
I didn't finish my sentence, but now I will finish. My question was another one. My question was, no, this I don't doubt about that. My question was just ZDI versus PIMS, which means the normal standard basic ZDI as we all apply versus the PIMS version. I would have enjoyed, and I would suggest you strongly to do that for your paper, to make a direct comparison between ZDI on one side, PIMS on the other side, or even a difference between both, just to show the added value of PIMS in that particular case. Because it's difficult for the reader to understand that PIMS is tremendously improving the situation versus ZDI.
So this is something we considered. The reason why we didn't do it was ZDI Pi is what I built PIMS off of, but I had to completely change the geometry of the code that they're using. So it feels like an unfair comparison to compare to ZDI Pi, because I'm not using the same geometry. There's a big difference here. What I can do in the future is make the modification to ZDI Pi to make it match my geometry. So I'm running off of there is pulsations, there are not pulsations.
Can't you just simply in your PIMS code disenable the pulsation aspect? Just to say, I don't want to fit the pulsations. I just do that. I just undo this routine where it stimulates pulsation. I just say there's no pulsation, and then it's the difference. When we don't care.
Yes, I can do that, and I don't know why I haven't thought about it first.
Okay. Let's now come a little bit to data reduction and so on, because I know that you did much more than what you presented here. with pyrreduce, adaptation of pyrreduce to neolava and so on. Let me just, can we see slide number 16, perhaps? This is about the results of Stokes V. One more. Yes, the upper figure.
Yes.
The Stokes V. It's difficult to see the typical S-shaped Stokes V profile. So I wonder, what do you think? Where does it come from? This atypical oscillation of? Is there any kind of idea?
So what my first guess is the wavelength calibration.
Yes.
Because for one of my observations, which I did not include in my thesis because the star I did not have a magnetic detection for, I ended up in one observation having two different eye profiles for the star. It is not a binary, it appeared once. If you took an observation very close to it, like we had other observations on consecutive nights and it was there and then it disappeared and never appeared again. That was due to the wavelength calibration being quite far from reality, and it caused a big shift of some lines in that order to create a completely new eye profile. If that's happening on a smaller scale inside here, inside a much smaller range, it's going to start scrambling this. So I'm going to see high amplitude signals that are going to give me a magnetic detection, but it's not going to give me a magnetic detection which looks like a wall. Well, that one's not particularly neat, but a neater magnetic detection, such as this one.
Yes. By the way, I know pretty well that the data reduction software, the official one, has tremendously improved in the last years.
Yes.
And that most likely all data sets are again and again reused.
Mm-hmm.
So it might be worth that, not now, but when you have a moment, that you try to download again, or that you ask directly Arturo if we have reprocessed them, and you might be surprised that some of the major mistakes are disappearing.
Okay.
Also, we can try one day to do the analysis with our own software, Dextra, and also with pyrreduce.
Yeah.
So it's very nice, very interesting. On slide 19, I'm almost finished. Just the lower figure of this page. I was astonished. I mean, it's probably my mistake. I don't understand the intensity profiles. Is it why are they so shifted? What's happening there? I mean,
so
it's not clear.
this one I think is an example of wavelength calibration being off, essentially because it's so far removed and it doesn't quite land with the same sort of temporal range as these. So this fall, you have a couple of them here, and then you have this one, and then immediately back to this range. So it doesn't feel like.
What are the time scales of the observation? Days, weeks, years?
This was all in a single semester, so 6 months.
6 months, okay.
So it's a bit odd behaviour.
Yeah, so
but also I don't really have an explanation of why the wavelength calibration would fully shift everything, except for maybe if the Earth's velocity wasn't missed overnight in the reduction, but I don't know how that would happen. So I don't really have an explanation for why that one's here. The variation in the line profiles are normal, actually.
okay, so it might be interesting that in your final version of your manuscript, you take into account a couple of comments on that stuff, and make it reread by your PhD supervisors. As a general conclusion from my side is don't be scared about the modifications I'm going to suggest. It's just that I think they will tremendously improve your manuscript, and there's no comment on the core of your work. It's just, in my opinion, some stuff to be done to make it more presentable, more readable, and to improve the quality of the presentation. Okay. Okay, thank you.
So thank you for that. So Victoria, we can move to.
Thank you, Chloe, for this very nice talk, and congratulations for this immense amount of work you have done. And I'm going to repeat actually a few things that Colin Thurston said. First of all, you really have to use the I word because you did the work. You really, because it's really not
it was really not clear from your thesis, but also hear what you have done, and you've done really a lot of work, and you should be proud of it. Okay, so I really encourage you to show, especially when you're searching for a postdoc position. This is very important to show what you have done. Okay. Having said that, I also agree that the written thesis, the thesis itself, requires a little bit of overdo, especially for a non-expert like me. Okay, I'm an astroseismologist. I'm not an expert on determining magnetic fields. I was missing a little bit of introduction. Things like, introduce me to the geometry, for example, right? Simple things. It's just, and you would actually like your thesis to be read by other PhD students, master students, right? Who love this kind of introductions, right? So to be pedagogical, if you want. I know it requires a little bit of work, but I think you would love it as well to go back in 10 years and remind yourself, this is what it is, okay? So, as I said, I'm coming from the astroseismic part, so I would like to discuss a little bit the first chapter, or the pulsators, let's say. Your thesis topic is OMB, or hot stars.
Yes.
How did you end up with that Scudi stars and Gamma Dor stars?
So, yeah, it's a really good question because especially the Gamma Dors came in the last couple of months whilst I was writing my thesis. It's only when I was looking a bit closer at those stars that I realised they weren't quite right. So the Delta Scuti was classified as an SVB. I observed it, discovered it was magnetic. We did the test reduction with more sectors, and these P modes appeared. But its temperature is so cold, you can't really expect it to be beta Ceph star. But there's the much more reasonable conclusion. Well, we know that Delta Scutis exist in this range when they're magnetic. So this seems like a nice conclusion there. To the Gamma Dors, one of them, if I go back to the slide, one of them is a B8 star. I hadn't spotted the 2011 paper when I first observed it. So I was like, E8, it's an SVB star, observe it, it's got a magnetic field, characterizing it, all good. I then start to read up more on it whilst I was writing my thesis, and then I go, oh, this is 2011 effective temperature. Oh, that's over 1,000 Kelvin cooler than it should be. This is getting to the point where it's getting closer to the Gamma Dor instability strip. And I knew from the Delta Scuti results that, well, we could actually expect it to be at a hotter temperature. And then actually K.R. Bell was the first one who actually had previously identified that one as being a Gamma Dor. This came from my Plato sample, so it was an A star. I didn't have anything more than an A star, so I was like, okay, it'll be a Gamma Dor then. I didn't think too much about my classification other than a Gamma Dor. And then we were going through the results, and it got a magnetic detection. You check it against the list, and it's a Gamma Dor. What? So I passed that over to John, who you know well, who took that spectra and did a temperature measurement on it. We also had temperature measurements from earlier work, but we wanted to do our own to confirm. And it's come back as being 9,000 Kelvin, which is also 1,000 Kelvin cooler than it should be.
So you said that this 9,000 is from spectroscopy? Maybe I misheard.
So the 2011 is from spectroscopy, yes, and so is the 9,000.
Because this is what I actually wanted to continue asking with the. You don't really say where you have the temperatures or the stellar parameters to identify your targets, right? As a P, as Gamma Dors, Delta Scutis, and so on, right? And especially the one candidate where it says an S. So what do you call it? Delta Scuti, I think?
Yes.
Right. So just by looking at the Fourier spectrum of pulsations, how would you know whether, when you say, okay, now let me ask differently. What would you say is the difference between a Delta Scuti and the beta Ceph star? and then SPB and the gamma torque. You wrote it, but I wanted to go for
So-
something specific.
Right, so the way I have classified them in my thesis was based off the spectral type. So if it's B9, it's well below the B3 we'd expect a BTSF to be at minimum. B9 is only slightly hotter than A0, where we would expect to find delta scutis. We also know magnetic delta scutis to be higher, that's why that classification was made. In reality, what I would think people should be classifying on in the future is actually what the excitation mechanism is.
Thank you for saying that.
Because you know, there's my work, there's Keegan's work, there's the work from Gaia. All of this is showing that these instability strips we have these instability strips. They're based off of models that don't include magnetism, some don't include rotation. There's a lot missing from them, which do significantly affect the positions of these instability strips. So you can't take a spectral type or a temperature and really honestly believe that this type of star is in fact this type of star without knowing what's happening inside that's giving you those pulsations.
I fully agree, and that's exactly what I wanted to hear, so thank you. So my suggestion would be, in future when you give talks about your topic, to be very specific how you classify when you say that, or maybe go away from saying it's a delta scuti, it's a whatever, say PMOS, which I think it would be easier because then you don't open the can of worms that you just opened, basically. Okay, thank you. Another question I have, and this comes from me not being like an expert, maybe it's obvious to you, but to me it's not. How do you get your uncertainties on determining magnetic field strength, like all these LSD profiles? When you say, oh, this magnetic field is significant or it's not, can you discuss this a little bit?
So if I go ahead here, this is actually a really good example. So we have the Stokes V signature, and then we have the null here, the null splat. So there's a false alarm probability calculated from that to start with. You can see in this one we have some deviations down. This was due to primarily, we think, condensation in the instrument, causing instrumentation polarization. So this would have either high uncertainties, quite a high false alarm probability, at which point it was slowed away. So that's what we have to start with. If I go actually over into my Kim slide, so we go from the Stokes V detection. We know we can calculate the L coming back from this. And then I believe, but to be honest, I do use it slightly as a black box. There's a spec pole flow, there's also the PUL codes that were used by the minor survey that do the errors based off of also probabilities. Correct.
Okay, so then, thank you. Along these lines, now that you discussed the uncertainties, so it's actually exactly the next question I had, so it's good that you have this slide. So the difference between the two curves, the dashed line and the blue line, is the one is taking into account pulsations. Please.
Same phase, dashed lines without pulsation, the solid lines with pulsation.
Okay, and then here is the question, is this significant?
So in both cases, they would both have sufficient signals to be considered a significant magnetic field detection. What we'd get is different values for it, because the value found as an integration across here. So the area we have here is different between the two.
Okay. So in other words, it's crucial to take this into account, but to what extent, I think what I'm trying to ask here is, does it depend on the amplitudes of pulsations, whether it's necessary to
the amplitudes and the geometries, essentially the extent of the Doppler shifts you're seeing in the lines.
Right.
So then also, I guess, the line width itself. Yes, it's something necessary, and technically I'd say necessary even for a single observation before it hits the PIMS code. If you're not taking into this account, if you have a single measurement, you're not doing pins, and you do it not considering the pulsations, then you're still getting an incorrect value.
So, okay, and then that's exactly what I'm after. So how incorrect? I know it's a case by case decision usually, but from all the simulations you have done, because you have looked in several scenarios, right?
Yeah.
Can you quantify that to say 50%, 90%, whatever, 10% of?
It's hard to quantify because it can be so different because of the amplitude. You can get anything between it's virtually the same. You don't really need to consider this to we're 100 Gauss out, we're 200 Gauss out, because
okay, so all bets are
yeah.
Okay, thank you. I also actually had the same comment. It's funny with like Kwani et al. Paper, because you said the HD, whatever telephone number, it's not measured.
No.
It's inferred based, and it makes a huge assumption that is that the model is correct. It's not just the mode identification, but also the Brand-Wieseler profile.
Yeah.
So that's a really important thing. One question. Okay, one short. Okay, so you said that for the LSD profiles, the line list is very important.
Yeah.
Right. So let's say for B-type star, because that seems to be like the average star you have, right? How many lines do you actually use?
It's quite sad. It's 100, 200, 300. It depends, how hot we're getting, but it's at the hot side, it's 100 lines, maybe even a bit less than that.
And then up to which V-SINI value can you actually go to still have unblended lines?
I mean, it depends on the line and the area of the spectrum we're talking about. Really, the issue with V-SINI doesn't come from the blending of the lines, such as the ability to be able to detect the magnetic field, because the threshold of the polar magnetic field strength we're able to detect scales with V-SINI squared. Before you're going to have lines spreading into each other, what you'll get is just not a magnetic field capable of being detected with the current instruments we have. So I can't quantify that answer because it's not something I can hit.
Yeah, it's all good. Thank you.
Thank you.
Okay, well, thank you, Chloe, for the very nice presentation. I also have to congratulate you as everyone else for your work. I mean, it's a truly impressive work. I was especially impressed by the work of James. Okay, I was very glad to that someone took the lead of this kind of evolution of the ZDI, and I was especially glad it was not me, you know. Thank you for this. Yeah, so that's a truly impressive work, and yeah, again, congratulations on this. I will try not to repeat the questions that were asked before, and because it would go on for a long time and collapse. Okay. So let's try to avoid this. There are a few points that we will discuss also at some point. We need maybe to sit down with Coralie and myself and discuss a few points. So I will try to choose wisely my questions then. Okay, so maybe I have one question from your introduction. So you very quickly mentioned that for massive stars, most people believe that the field is fossil field. And I wanted you maybe to elaborate a bit on this. What exactly are the hints that make you believe that this?
So it's largely the stability. So we've been able to detect magnetic fields for about 70 years, a bit longer than that. It's a bit shorter when you take into account being able to not only detect magnetic fields, but be able to detect the slightly weaker ones and with a relatively good accuracy. But what we're seeing is there's no significant global change in the field strength. So there's been works that have shown small variations in multipolar components in a couple of stars now, I think. But the overall field geometry and strength stays the same over the timescales we've been capable of detecting, which implies it would not be a dynamo field.
Yeah, so by analogy with the solar or stellar dynamo, okay, which has typical timescales that are compatible with the mixing timescale of convection. So why would you expect a similar timescale to occur in a radiative zone? Well, why would you expect that the radiative dynamo would be also affected by some sort of phase variation?
So we don't really have a solid conclusion on that one. There's other work that's happening that does model radiative dynamos. I believe they are showing that there are longer timescales than with the convective solar type. But what we decide usually to go off of is just Occam's razor. If it's not changing, it's a fossil field. The changes we're able to see across the mini sequence are looking at stars that have just formed versus the orders of very, very slow decay, are changing, from multipolar to dipolar field. So it does change, but it's just settling down into what we largely detect and staying around that point. So it's we're not seeing young stars with super weak fields. We're seeing old stars with super weak fields. But super weak is probably a bad way of phrasing it because that's used for cooler stars that actually have weak fields. But in the scale of these, we're talking 300, 200. We see that in old stars, not in young stars. If we had dynamos, we'd expect surely that the field would not vary so strongly with age. It would be random.
Okay. Okay, thank you. Let me think, yeah, because I need to skip a few words. Okay, just maybe if you can just go quickly, I just want to, that was a comment that was already made, but slide 17 maybe, 17 is a good example, I think. Yeah, okay. I just want to, yeah, this one, I just want to, yeah, that was already mentioned, but there is very little chance that this kind of a signature you see in the bottom panel, especially, is actual Zeeman signature. So
it's included purely because it comes out as significantly statistically significant. However, I don't like to draw such a solid conclusion, especially on that star, because the eye profile is so wide, even with the wavelength calibration having errors. If the errors are that big to cause that much of an issue on that star, why would we not see it on others? Yeah. That one's one I'm very precarious on.
Yeah, because we were discussing about fossil field against dynamo fields. I mean, I see this kind of signature. I say congratulations, you have found a dynamo field in C stars. That's completely different. So, but again, as Torsten said, I mean, the data reduction is quite significantly better. Everything has been very reduced 1 year ago, and I invite you to download the latest version. Okay, for this. Okay, now I have a few questions on your work with pins, in fact. Okay, because I was excited to see this tool, and since, well, as already emphasized by several people, since you maybe don't put all extra material into your manuscripts, sometimes there are some questions remaining, so maybe I have a few of that. My first question is the following. Now that you have a tomography code that is able to model velocity fields on stars, I was wondering if, I'm absolutely not an expert in astroseismology, I was wondering if in this landscape it would be a useful tool just to characterize pulsations. You forget about parametry, you just keep the Stokes-Pie modeling and you characterize the modes.
So yes, I would like to say this wouldn't be the first tool that exists to do that though. There was a ZDI code, its name is Inverse, I think 13 was the version that included this. It included velocity mapping. It was used to show that rho AP stars, their pulsations are more closely aligned with the magnetic axis than the rotation axis. So this code wouldn't be the first tool that is available for that. I'd also say that tool is better than PIMS for this, because at least in the current version, PIMS is reliant on you providing the pulsation modes. So you're essentially going, I know that the velocities are like this, fit the velocities like this. It's not quite the right tool currently. The way I see this developing in the future is to do mode identification in place, at which point we'll be removing that requirement and allowing the velocities just to be fit as, well, I imagine first as in the coherent way that we currently understand these hot stars that pulsate, but then we could allow it to potentially, a step again in the future, not to confine it to a single geometry. But this is not where the code is at the moment.
Okay, thank you. Now, well, this is, I'm getting close to a comment by Vicky here. When you present simulations to test PIMS, okay, you try to investigate when you get errors from ignoring pulsations and when it gets better in the pulsation. And I have maybe a more general question. Can you try to list exactly at which steps in the ZDI inversion you do errors? Because I mean, that's a model, okay? And, so, and before ZDI you have LSD, okay? So that's at least two models between you and the data, okay? So when you think you have error generated in your inversion?
I mean, there's risk of error in LSD, but assuming all the normalizations done correctly, all the lines are nicely picked out, the error there should be minimal. The error here comes at multiple levels of it. There's error that's going to be occurring due to the fitting of the pulsation modes. I think if I have the table, yeah. So
well, you have at least one error also with LSD, which is that LSD intrinsically relies on the weak field approximation.
Oh yes, and so does PIMS, the magnetic field detection.
And so does PIMS, okay. So of course, I mean, you have fields of a few hundred loss, so that's not critical. I mean, what was presented, but I mean, there is no strict limit. Okay, people tend to say, okay, above 1 kilogauss, that's not a weak field anymore. But I mean, it's a strict limit, and you make an error, a limited error, but you still make an error.
I believe there was work done by Colin Falston, who built the ZDI PyCode, who tested the weak field approximation for these type 4 stars to go up to about 10 kilogauss.
Yeah.
So in theory, everything we detect, even if we're to go for the ones right at the beginning of the main sequence, which sit more at 8 kilogauss, we should be well below that for everything we're doing, theoretically. That's why I'm not so concerned about the LSD error. I mean, I guess there's also LSD error from potential line formations at different regions. That's what we're seeing in helium-2. But I'd say the major error is actually coming from the PIMS code, if I am completely honest. The comparison between what I provide and what ends up being fit, you do get small errors, but that can then stack up. If this is for 3 modes, then you extend down, there's more modes. You're going to have an increase in the errors that way. The errors here will then affect the brightness map, which multiplies the errors, which will then affect the magnetic field, which multiplies the errors again. So
okay, and this is with simulations, so that's the easy case, okay?
Yeah.
But now using real data, what additional errors can you make in this case?
I mean, it's subject to the same errors of, you know, if your mode identification is incorrect, if your LSD models are not ideal, if the code has an error in its fitting, then obviously pulsations and the velocity, it then multiplies for each subsequent step. So there's plenty of opportunity. The way I give error bars is right at the end, and I just iterate over inclination because there's really no great way of quantifying it.
Visceral? as well? I mean, you know, B-cyanide.
So B-cyanide is not so big of a contributor, just because I have this extra line width factor that allows the B-cyanide essentially to change a bit.
Yeah, but it changes, yeah, your extra broadening will help you fit the data anyway. But if that's attributed to the local broadening and not to B-cyanide, that will change your geometry.
Yeah.
Okay, so all in all, well, how much, I mean, and that's again close to the comment by Vicky. So what would you say, at what threshold would you say would you start to believe that you actually start to make a significant error? I mean, what you get is above all the errors you cannot avoid, okay, in the version.
So can you repeat the line?
Yeah, when you consider, I mean, given that there is a number of errors that of uncertainties in your inversion, when would you consider that what you get with PIMS against what you get with a standard ZDI inversion becomes significant?
What I would say is, if ZDI pi looks like the better option, we're in big trouble, because ZDI pi just in general doesn't converge with stars. So if
it does not converge, you should try to adjust the Stokes time, but you could also
but if
not even try.
okay, if I was to give it a uniform brightness map, then it sure does look okay. But if PIMS is giving a similar result to that, then what we're getting is either very low amplitude pulsations, which you can check by looking what mode parameters were fit, or we're getting complete nonsense. What's also useful to look at is, as I did the brightness map, because the brightness map in both ZDI pi and PIMS really starts to make it obvious where errors are being introduced.
So for my personal experience with ZDI, okay, there is not a lot of documents stating explicitly what could be considered as a reasonable uncertainty on ZDI inversion. Okay?
Yeah.
To my knowledge, there is one paper stated explicitly. This is Vigoto et al. 14. And what is stated in this paper is that the uncertainty on ZDI is typically a factor of 2. Okay, on the global magnetic field strength. So exactly what you call the Dipler field. Okay, so factor of 2 meaning that an error of plus 100% and minus 50%. Okay, so that's and in fact very recently that's what I tried to do with a student. We took a Spiro dataset that was published, okay, and just made an independent modeling, and so that was independent LSD, independent ZDI, not exactly not the same ZDI code, in fact. That was a factor of 2, but that was 20-30% difference, just because that were two researchers doing their best, to invert the data. So my point, and I think bearing that in mind, in new, what is this slide again? That's slide number 59, 49, sorry. Yeah. I will yeah, sure. In this one, okay, you sometimes get a very large number of observations required if you want to do a clean job. And my question is, what is the metric you use here? So when you say this is what we need to get a clean job, what kind of error do you allow here in your inversion?
If I remember correctly, it was about plus or minus 10%.
10%. So meaning that in fact that's extremely strict that
Yeah.
which is a good news, because it means that in the end you don't need probably to collect that many phases to get a good job. Okay. That's it for me. Thank you.
Thank you very much. So thank you, Chloe. And then now it's time to have comments or questions by your supervisors. So Claude.
Thank you. So, dear Chloe, of course I will not ask you the question. I might repeat some comments that were already made, but first of all, I would like to congratulate you for these 3 years of hard work. People have already said that, but perhaps Coralie and I, well, we know better how hard it's been. It has been hard all along, but more particularly so in the last few months. We know that it was quite difficult for you. But in the end, you made it. Yeah? You made it, you have proof today. So I want to congratulate you on that. You were able to fight successfully perhaps the most terrible enemy of any PhD student, which is time. And you fought against time, and you fought successfully against time. You learn how to tame time, if I can allow myself this kind of word in a language which is not my own. Something which has already been said, the problem you have addressed is very difficult. It's a very difficult problem. That is Zeeman Doppler imaging in presence of pulsation, or more generally speaking, in presence of velocity fields, local velocity fields at the surface of the star. I suppose that if the problem was not so difficult, of course it would have been solved long before. We had to wait for you to solve it. So thank you for doing it. And as was already been said, it represents a tremendous amount of work, both for developing the method, which you have called PIMS. By the way, I congratulate you also for the name. It's a very nice one. Both for that and also for gathering and analyzing all the data, which is necessary for this. Now, concerning the amount of work you have produced, something which was already mentioned, and want to emphasize this, which I think is important. In the course of your thesis, you discovered that some of the data you had to work with, indeed some neo-narval data, were suffering from reduction problems, what you think are reduction problems. And sadly, this problem affects strongly the spectra of hot stars, particularly in the blue part of the spectrum, which is unfortunately where most of the important types are located. So at some point during your thesis, because you knew you had to work with those spectra, you decided, or rather we decided together, that you, with the help of Keegan, get that, you would spend some time trying to overcome this problem. So you worked really hard on this, and you spent more than, let's say, half a year, probably, several months at least, several months, at least several months full time, developing some new reduction software to overcome all these problems. But sadly, you found out that the problems were a bit more complex, a bit more severe than we had anticipated. And so in the end, you could not finish on time for your manuscript, nor for your defense. So I just wanted to say that. So you have done much more than what we have seen in your manuscript and what we have heard today. But I am 100% sure that this will eventually have a positive outcome, and that it will require more time and more effort. Of course, at the end, all the time you have devoted to trying to solve this problem, all this time you missed badly at the end when for completing your manuscript and preparing your defense. But as I said before, you made it. So we have a happy ending here. So again, I want to congratulate you for your, in spite of all these problems, for your success and for presenting us this beautiful work today. Thank you.
Thank you, Claude. And Coralie?
Yes, just to finish, I think Claude has already spoken very well for both of us. And I fully agree with the amount of work that you've done, and not everything is in your manuscript or shown today. But I would like to also add that the work you've done will be very important for the future. You mentioned Plato, you mentioned magnetohysteroseismology, and this is really great preparation for this next step that I hope you will also undertake in a few years once we get Plato data. And so we don't know yet exactly where you will be next year and how you will continue, but I hope that you can find some place, some position that suits you and where you can continue this nice work.
Thank you, Coralie. So I have a question from someone who is completely out of this field, because the feeling I have and the impression I had with your presentation is exactly what all people who are here, who are much more expert than me, said, that it's an incredible amount of work, and also you also show really that you have understood and you master everything you have done. But I had that curiosity because there is also the work you have done to me requires also many different skills, because you have gone through observation, requiring observational time, reducing data, but also writing and developing a new code. So can I, just for curiosity, how did you organize the work? Was the piece work done in parallel with the first part of the work you present, and where did you find the, well, we understood about all the challenges you had, for example, with neo-narval data, but are there other challenges that you faced that were particularly difficult or that require time during this period?
The observation side of it, that was running parallel to everything I was doing otherwise. With regards to the PINS code and then the second code, which was not included in my thesis, we've now named it Magpie, but it's based off of a code called Pyreduce. Those I kind of alternated between, especially because so PINS is what I was presenting at conferences, so I tended to work around it in the lead up to conferences, and then I'd switch back to Pyreduce, and so it was a lot of work to balance between the two of those, and then periodically I was like, oh, and it's time to do another observation proposal. And I guess what I found particularly challenging about it was, I mean, beyond the workload and the different things I was balancing, I came from a background where I hadn't done astroseismology before. I had worked on magnetic fields back in my master's thesis, but I was working from the results of ZDI, so I didn't know anything about spectropolarimetry, how to reduce spectropolarimetry, how to map those magnetic fields. So I had a very steep learning curve the first couple of months, but I got amazing support from my supervisors on that.
Thank you, Chloe. So thank you very much. I need to ask, before we deliberate, if there is someone in the room who wants to ask questions. Apparently only people with PhD can do it. So if there is anyone who wants to ask a question, it's time to do it. No? So if so, I think we can...
Thank you very much. C'est la seule délibération. En principe, c'est la We're going to go stretch away now. If we need to be anywhere else, I'll let you know. Right, hang on.
That it was just really for her to be able to watch that.